Welcome to TADSummit. It's my pleasure to deliver this keynote. Obviously, I'd rather do it in person, but, well, we all know what the past year or so has been like. Anyway, I want to talk a little bit about an aspect of connections that is sometimes neglected. The industry talks a lot about the how, and later in this conference you will hear a lot about the specifics and the how to connect the stuff, including from Michelle and Lauren from Telstra. The how is of course important, but this is not a talk about those specifics. This is a talk about the why and about the so what. For years, decades even, the entire industry has been about connecting stuff. Quite naturally, given it's the communications industry, right? I worked for a number of years for Nokia, and their slogan at the time was connecting people. Later on, as IoT has become a thing, we've become obsessed about connecting things, and the new rule of the industry seems to be whatever can be connected will be connected. What I like to ask is why, and also what could possibly go wrong. This is not actually a rhetorical question anymore, because things have indeed gone wrong. Anyone remember Cobra Bubbles from Lilo and Stitch? Before we talk about how our incessant drive to indiscriminately connect everything has led to things going wrong, we need to take a step back and consider some theory. Meet Charles Perrow. He's an American professor at Yale and Stanford. Perrow is also the author of the book called Normal Accidents, Living with High-Risk Technologies. Published over 30 years ago, it explains the concept of what he calls normal accidents, catastrophic accidents that, he argues, are inevitable in tightly coupled and complex systems. He thinks that in complex and tightly coupled systems, failures will occur in multiple unforeseen ways that are virtually impossible to predict. To help us think about this, he also developed what is now known as Perrow's matrix. Perrow's matrix is about mapping systems according to two factors: coupling, whether it's loose or tight, and interactions, whether they are linear or complex. Before we go on to look at what the world looks like according to this model, let's take a quick look at what exactly do we mean by interactions and coupling here. Now, any two-axis model is, of course, a gross oversimplification of the world. However, there are some distinct system characteristics that arise when we look at things from interactions and couplings point of view. First, let's look at interactions. Linear systems are highly structured systems that are logical, sequential, and planned. A series of events takes place in predictable sequences. Minimal feedback loops exist. Complex systems, on the other hand, are less predictable. Subsystems can behave unpredictably because of unplanned and unforeseen interactions. There is a need to rely on incomplete and often indirect indicators to assess most situations we simply cannot understand at all. And problems, as a result, are not easily identifiable. One important point to remember is that the difference between complex and linear systems isn't sophistication. You can have highly sophisticated linear systems. It just depends on what kind of things we're discussing. Then on the coupling axis, loosely coupled systems are characterized by decentralized operations and flexible control mechanisms. Change has little effect on these kinds of organizations, and such systems are flexible and resilient in emergency or abnormal situations. There is slack between the parts. When one part fails, it does not necessarily reflect in other parts immediately. Tightly coupled systems, on the other hand, are highly centralized and rigid. There's little slack between the parts. Output is closely monitored within specified tolerances. There are interdependent subsystems. Change causes massive ramifications throughout the system. Tightly controlled time schedules with little tolerance of delay and substitutions are not easily accomplished. You may also wonder what we mean by the word system here. I mean, a system can really be at any scale we wish to analyze things on. A transportation system is one high-level system. A car manufacturing facility is also a system, so is obviously a car, or the brake subsystem of the car. Before we get back to the matrix, I want to make one point about complexity. Arguably, anything we infuse with computers become complex systems. As Quinn Norton pointed in a classic article some years ago, your average piece of shit Windows desktop is so complex that no one person on earth really knows what all of it is doing or how. And herein lies one of the major problems. As connecting things in a technological way almost always means that they get, in a sense, multiple computers embedded into the system. So what does the world look like according to this model? So this is how various systems today map onto the matrix, or rather, how they mapped onto it some decades ago. While this is not a comprehensive selection of systems by any means, they are mostly evenly spread out. If anything, the top right-hand corner is a relatively sparsely occupied region. And it is that top right-hand corner we now want to focus on. That corner is the so-called danger zone of complex and tightly coupled systems. They are, in a way, inherently dangerous. Think of the other quadrants. When you have a complex system that is loosely coupled, stuff can go wrong, but it doesn't result in a cascading failure because of the loose coupling. There is slack and usually time to recover. On the other hand, when things are tightly coupled but linear, they're easier to model, easier to understand, easier to keep under control. Any failures are far more predictable. Of course, linear and loosely coupled systems are the easiest of all to manage and the safest. Now, there didn't used to be too many systems in the danger zone, but what is happening now, or what has happened over the recent decades, is that systems of all kinds are moving into the danger zone. For some of the systems, such as finance, the move makes intuitive sense. We know financial systems are now highly interconnected and automated. We hear of flash crashes caused when high-frequency trading algorithms do unexpected stuff and so on. Since Perot's initial analysis, many of the systems he had classified as linear or loosely coupled have become complex and tightly coupled. All sorts of systems are now moving to the danger zone. Now, Perot's analysis has come under some criticism. As any such simplistic quadrant methodology, it of course is not perfect, but it does allow us to think about systems in a bit of a different way, and we can learn about that. Over 30 years after Perot wrote Normal Accidents, Clearfield and Tilksig revisited the topic in their book Meltdown. It clearly lays out the risks in a more modern context. When we begin to realize things that could go wrong, our natural inclination is to add a safety system, a warning of some kind that alerts us when something is going awry or prevents things from going pear-shaped in the first place. There's a bit of a problem with that. Not only can a safety system not warn you when it no longer can warn you, i.e. it has failed, but also safety features themselves become part of the system, and that adds complexity. As complexity grows, we're more likely to encounter failures from unexpected sources. It gets even worse, because complexity also creates opportunities for wrongdoing, and tight coupling amplifies the consequences. We won't talk about that too much here, but think of Enron or Theranos or even Bernie Madoff. It is the complexity of the systems that allowed these scams to take place in the first place and to thrive for so long. So we get to the pointy end of stuff. The first question we need to ask ourselves is, do we really need to connect everything? Clearly the answer is no. I bet you can think of a few things that have been connected, which really would have been better off not being connected. One of these things could be fridges. The appliance industry has tried to push the concept of a smart fridge for years and years, and it has never really taken off. These expensive devices have little to no benefit, but do have a bunch of downsides. Another thing that probably usually is better left unconnected are toys. Here too, smart toys have resulted in the kind of privacy breaches we really don't want to happen. But things go wrong at the big end of town as well. This is a dam. We all know dams. They seem pretty simple systems, right? What could possibly go wrong with them? Let's compare the dams of last century to dams today. So dams 30 years ago, they had an on-site dam tender. The connectivity was a telephone line. They operated manually. They had locally controlled gates and switches. And if you wanted to know what's going on with the dam, the person walks the dam and looks at what's happening. Dams today, there's nobody there. Connectivity is real-time IP-based. They're remotely operated. They're remotely controlled. Inspection happens via sensors. So the characteristics have shifted quite a bit in the past decades. So you can probably see what's coming here. At a California dam, for example, when a position switch fell off a gate, the remote operators got confused about the gate's position and didn't realize how much water they were releasing. People were stranded downstream, and though tragedy was avoided, it was the beginning of a classic systems accident. All it took was a small mechanical failure and a misleading indicator, and the system was soon slipping out of control. There are countless other examples, But this is where we find ourselves at. To be alive in the 21st century is to rely on countless complex systems that profoundly affect our lives. Systems that were once innocuous can now accidentally kill people, bankrupt companies, and jail the innocent. So things can and do go wrong. And I think we can agree that not everything actually needs to be connected. Metcalfe's law doesn't magically bring value into networking stupid things. But aside from choosing not to connect something, the next question we need to ask ourselves is, what can we do? What can we do to make sure things are at least as good as we can make them? So thankfully, there are a lot of things we can do. These are just some of them based on my research into the topic. They come in a variety of categories, from practices to specific tools and even regulation. There are too many to look at everything here, so we'll take a brief look at just a few items. First, let's look at pre-mortems. They are a simple thing to do and very generalizable. Whether you're about to embark on a long car journey or start a new product project, it's a useful practice to conduct a pre-mortem. Guy Kawasaki can explain this succinctly, so let's let him explain that.
You should conduct a pre-mortem as opposed to a post-mortem. A post-mortem is something you do, obviously, after death. It's done to increase the peace of mind of the loved ones of the deceased. The problem with post-mortems is, it's too late. There's another problem with post-mortems. Post-mortems in business is really too late, because by the time a company implodes, most of the people have scattered to the winds. They're not going to stick around to the bitter end. Okay? And even if they stuck around, a post-mortem is very contentious. You know, you bozos wrote a piece of crap, as opposed to you bozos couldn't market this brilliant piece of software that I created. A lot of finger pointing, a lot of angst and anger. I suggest you do a pre-mortem. And the way a pre-mortem works is, before you ship, you ask the team, let us pretend that our product, our company, failed. We failed. Now, what are all the possible reasons we could have failed? Lack of distribution, unsophisticated sales force, buggy software, unreliable cloud services, whatever it is. So you come up with all these reasons, and then in unemotional ways, you talk about how you can eliminate each of those reasons. This is very different than pointing the finger and saying engineering is crap. Okay? What you're saying is, this is a list of reasons. Let's conduct a pre-mortem so that we never conduct a post-mortem. Conduct the pre-mortem.
Next up, we have a tool that seems ridiculously simple, but has been proven to be effective. A case where the acronym was landed on before the actual term, probably. I'm sure we're all guilty of that, called SPIES. We can use SPIES for improving predictions, whether we're talking about market forecasts or probability of a sensor failure or even an effort estimate. The point of SPIES is, rather than asking people to estimate, say, the failure rate, people are asked to do the same in intervals. It's been shown that this increases accuracy markedly as people put more cognitive effort into thinking up the probabilities. It can, in fact, more than double the accuracy of your predictions. Then there is culture change. Needless to say, that is not an easy thing and something the whole industry would need to work on together. The ICT industry and startups have talked about embracing failure a lot in recent years. So we increasingly talk the talk, but that's where it often ends. Without the next steps, without feedback and institutionalizing the learnings, our experience or our mistakes do not make us into better decision makers. And our industry broadly lacks the supporting systems or the scaffolding to embed that into everyday activities. So by openly sharing stories of failures or near failures without blame or revenge, we can create a culture in which people view errors as opportunities to learn rather than as impetus for a witch hunt. And man, there is a lot to learn from them. While not all public reports need to be named, NASA's ASRS, for example, does not include operator names and irrelevant details. Inside the organization, anonymity is not desirable. Anonymity can backfire. The emphasis on anonymous reporting can actually highlight the dangers of speaking up. The subtext here is that it's not safe to share your views openly in this organization, hence we need to be anonymous. We need our equivalent of just culture. It's a concept related to systems thinking which emphasizes that mistakes are generally a product of faulty organizational cultures, processes, and procedures, rather than solely brought about by the person or persons directly involved. The main difference is that it seeks to make the systems better, not to punish individuals. It's common among aviation operators and has increasingly been applied in healthcare settings as well. Now, in aviation, there's a system called ASRS, Aviation Safety Reporting System. It's run by an independent unit at NASA. It collects thousands of reports every month from pilots, military operators, air traffic controllers, mechanics, and anyone really involved in the industry. They also highlight safety trends and interesting incidents and close calls in the monthly newsletter callback. We also need somehow to build such a public collection of case studies, public learnings, and public feedback in our industry. For without feedback, experience doesn't make us into better decision makers. We need to institutionalize learning better. The critical part is that we need this to be open. This is stuff that cannot be learned in secret. It's important to recognize here we can't just make systems better and forget about learning from mistakes. As we've seen, a fundamental feature of complex systems is that we simply cannot find all the problems by simply thinking about them or even trying to analyze them. But such complex systems do give off warning signs prior to failing. To learn to manage the complexity, we need to learn from the information our systems throw at us in the form of small errors, close calls, and other warning signs. Now, granted, there are baby steps to building something like this, but they are, for now, very narrow solutions with limited uptake. The best example I have found in our industry is the AI incidents database, which seeks to collect things that have gone wrong with AI systems. They explicitly express the desire to become the ASRS of the AI world, and time will tell how that's going to be adopted by the industry. But overall, these systems are lacking, and the supporting culture just really isn't there. Lastly, let's talk about Slack. Not that Slack. There are benefits from loosely coupled systems. Components in a loosely coupled system can be replaced with alternative implementations that provide the same services. Components in a loosely coupled system are less constrained to the same platform, language, operating system, or built environment. Tightly coupled architecture is fragile, as the minor issue in one segment can bring the whole system down. It is, however, not a panacea, because obviously there are also drawbacks to loose coupling. If the systems are decoupled in time, it is difficult to provide transactional integrity. Additional coordination protocols might be required. Data replication across different systems provides loose coupling in availability, but creates issues in maintaining consistency or data synchronization. On the process side, we've seen that tight coupling is risky. Therefore, it's a simple suggestion to engineer Slack in and avoid tight coupling as much as possible. Yes, you will sometimes lose some efficiencies, but it's worth asking whether those efficiencies are worth the potential failure points. Now, many of these strategies can be thought of as adding inefficiency. That's actually not just a bad thing. It's an important thing, because efficiency creates brittle systems. Bruce Schneier made this argument last year that our systems need more inefficiency. But it's not about making systems wasteful. We need certain kinds of inefficiency, and it depends on the system what kind. Sometimes we need redundancy, sometimes we need diversity, sometimes we need overcapacity, and sometimes we need slack. With that point about inefficiency, it's time to draw some conclusions. There would be many, but in the interest of focus, I have chosen 3 main points, which I hope are, dare I say, actionable. The first thing to remember is that a connection is not intrinsically a good thing. Metcalfe's law doesn't magically create value if we connect the wrong things. A smart fridge, for example, may sound like a great idea, but is it really? After we know that we've connected the right things, we need to think about if we're connecting them right. Because as we've seen, there are worse ways and better ways of doing that. If you're going for the cheapest IoT device you can find, you'll probably find that it's not the right thing to do. It's most likely insecure, it's most likely non-updatable, so it's far from future-proof. As a rule, remember that the S in IoT stands for security. Connections are often about coupling. But on the other axis of Perot matrix, you'll remember we had complexity. As we've also seen, the more complex our systems, the more inherently dangerous they become. Therefore, embracing simplicity and purposeful inefficiency are important design principles. Another thing we need to embrace, as we just discussed, is purposeful inefficiency. If 2020 has taught us anything, is that our search for efficiency has gone too far in many cases, whether it's global supply chains or medical care capacity. Finally, culture change is something each and every one of us can play a role in. Yes, we need to build the supporting frameworks as well, but at least all of us can and do have some say on how we build culture. We need to shift our attention away from individuals and from hiding mistakes, punishing people, to learning from them and focusing on making our systems better, safer, and more resilient. So with that, we'll wrap it up. If you only remember three things, make it these three things. Be mindful about the connections you make, embrace simplicity and inefficiency where it makes sense, and do your part to change the culture. Also, feel free to reach out via any of these regular channels.